Hey, it's Brian. Here we are at the end of the semester for Physics 122. And do you remember back at the start of the course, I said after we do the electricity and the magnetism and the induction and the quantum mechanics and the nuclear physics, we're going to talk about light. We're going to talk about light and optics. And light and optics is my favorite topic of the whole course. And it's a really, really great way to finish because it's interesting. It's not conceptually that challenging, and there's a lot of wonderful applications. We are here in our last 3 weeks of the course. We're going to be talking about light, color, and optics. This is my favorite material of the whole course. And we're going to start by talking about wave optics and the things that happen to light that explicitly take account of its wave nature. That's where we're going to start. And the type of thing we're going to consider is this. If you've ever seen a hummingbird in action, you know that they have these colors that flash. The colors are actually brown, but once in a while, at exactly the right angle, with the sun in just the right spot, you'll get flashes of color. You're going to get reds here. You're going to get greens here. This is an example of what's known as structural color. It doesn't come from pigment, it comes from the way that structures are made on an atomic scale. And this is the type of thing we're going to be looking at this week. So let's talk about this concept of diffraction. And actually we looked at this before. We looked at it in chapter 15 when we were first talking about waves. When a wave goes through an opening, it spreads out. That's the diffraction. You can see I have like straight lines of waves coming in before the opening. Afterwards they're more circular and there's a spread to them. And it spreads out at some sort of an angle behind this opening. That's the concept of diffraction. Have some interference associated with it. And if you look in this picture here, I can start to see it. So look at this image right here. You can see the light, so you can see water waves which are going through. Now if we look at a diffraction pattern, and here's a diffraction pattern, I've got light coming up, hitting this barrier here. And when the light hits the barrier, it subsequently spreads out. And you can see there are places where the light from, or the waves from this side and this side, as they spread out, there are places where they overlap and you end up with bigger waves, and then there's places where the waves are sort of like wiped out. You have places like this. And then I've got shadowy waves out here. And so I can end up having a pattern where I have the waves constructively or destructively interfere in the region behind the barrier. And that's adding the concept of interference to the concept of diffraction. And that's where the most interesting effects come in, because we've seen before this concept of interference. If I've got like sound waves from two speakers, there are places where the waves will reinforce each other. Okay, like right here, I'm going to have a loud spot there. There's also places where they will cancel each other right here, and I'll have a quiet spot. So I end up with regions of constructive and destructive interference. We'll have the same thing with diffraction patterns with light, and that's mostly what we're going to be interested in. And if I have a diffraction pattern with light, I can have the light spots and I can have dark spots corresponding to regions of constructive and destructive interference. Now the way we'll make diffraction patterns, and you'll get a chance to play with this doing simulations, is this. We're going to take light, and we imagine here we have some sort of a laser beam coming in like so, and it hits some sort of a barrier with two slits in it, and I get diffraction from each of these slits. And as a consequence, I end up having two sets of waves that emerge behind this slit, pair of slits, and so you end up having regions of constructive and destructive interference. And so on the screen I get regions where there's light fringes, and I get regions where there's dark fringes. I get constructive, destructive interference. I will have a video that you can take a look at that shows a bit about how that works. And we get it not just from double slits, we get it from gratings, we get it from single slits, we get it from circular obstructions, we get it from other kinds of obstructions. I want you to pause and I want you to take a look at this, because some of the phenomena are much easier to understand once you're able to visualize them. So go ahead and take a look at this extra video. Go ahead and pause right here. Take a look at that one on diffraction patterns, and you can take a look at some of the phenomena that we're going to be seeing in these slides. So let's look at an example of how we make a diffraction pattern. So I've got this double slit over here, and I've got light coming through this double slit, and I have regions of constructive interference where I get bright fringes. I have regions of destructive interference where I get some dark fringes. And typically I will look at the bright fringes. And the central maximum I'm going to label with this index m equals 0. That's exactly straightforward from the double slits, not at an angle at all. And then I get subsequent bright fringes out to each side, and I have an index variable that goes out from the center. M is equal to 1, m equals 2, m equals 3, m equals 4 for the successive fringes. I get another set out the other side. M is equal to 1, 2, 3, 4, etc. This is my double slit interference pattern. If, instead of having 2 slits, I have a whole lot of slits, I end up getting a much sharper pattern. So instead of having fuzzy bands, like I have right here, I have really crisp, well-defined bands. And that's when I have a lot of slits. This is what's known as a diffraction grating, when I have that many slits. More slits makes a sharper pattern, and that's typically the kind of thing we're going to use for analysis of wavelengths and such. Now, here's the basic relationship we're going to have for diffraction gratings. If I have light of wavelength lambda approaching a grating, and there's a spacing d between the slits of the grating, and so I have like a pattern of like spaces where light can go through and where it can't. The spacing of the slits is given by this variable d, okay? And then I have a distance L that a screen rides behind the slits. I end up getting light and dark fringes. M is the index variable, so I get m is equal to 1, m is equal to 2, m is equal to 3, etc., etc. And I measure the distance from the central fringe by this variable I call y, okay? Those are the way I label those variables. And there's 2 different relationships we're going to use for those variables. One is this. If I look at the angle at which I have constructive interference, I have a series of angles, and they're going to be this. The angle theta m is the angle of the mth fringe. So for m is equal to 1, it's the angle of this m equals 1 fringe right here. It's the angle from the center line. That angle would be theta 1 right there. That angle, d times the sine of that angle, is equal to m times lambda, where m is the index variable. So you can see I get several different angles for several different fringes. The position, or the distance from the center of the pattern to the mth fringe, is given by this relationship right here. Ym, the distance of the mth fringe, is equal to L, the distance to the screen, times the tangent of theta m. Now I want you to know, in the book, there are different sets of equations for double slit patterns and diffraction patterns from gratings. Don't worry about the double slit equations, just use the ones right here. This set of equations will work for double slits, it will work for diffraction gratings. It's going to work for everything. So just use these equations here. Don't worry about the double slit equations. We give out a lot of these rainbow glasses in the Little Shop of Physics, and inside these there are lenses that have a bunch of different lines, and they go vertically, and they also go horizontally, and they break light up into a spectrum. We call these rainbow glasses, and we give these out by the tens of thousands. I've probably given out 500,000 sets of these glasses over the course of my career. If you're interested in a pair, you can contact me, and I will definitely set you up. And my intent was that during this section of the course, we're going to be basically looking through rainbow glasses every day, because we're going to be talking about wave optics rather than just talking about it. We're going to do it. We're going to see it. So if you want a set of glasses, let me know. I'll set you up. Now I want you to think about this. If we're using the rainbow glasses, okay, and then you put them on and you look at a source of white light, different colors get bent by different amounts, and so as a consequence we produce a rainbow, which is in fact why we call them rainbow glasses. Here's my question. If I use the rainbow glasses to look at white light, I'm going to break the light up into a rainbow. Is the red on the inside closer to the 0th order, or is there blue on the inside? I want you to think about the basic relationship for diffraction gratings. I want you to come up with an answer, and then we'll talk. Well, if we look at our basic relationship for the angle at which the different orders of diffraction appear, it's this. It's d times the sine of theta m is equal to m times lambda. So if the wavelength gets bigger, the angle gets bigger because everything else is going to stay the same. So if I'm looking at the m is equal to 1 order, okay, theta 1 will be bigger if the wavelength is bigger. So red light will appear further out in the pattern than blue light. So it's going to be blue on the inside and red on the outside. So this is the right choice here. And blue on the inside and red on the outside sounds like, I don't know, some sort of a metaphor or some sort of a poem like that. But in this case, that's the way the rainbow is going to appear. Now here's a question for you. If you take a pair of these rainbow glasses, such as we give to children all over the world, they have 260 lines per millimeter. Okay, suppose I took my laser pointer, which has a wavelength of 530 nanometers, and I shine it at the diffraction grating in the rainbow glasses. I'm going to get a diffraction pattern on the screen. We want to analyze that, and for the first part of that, we want to do this. You're typically given not the grating spacing d, which is what we use in our equation. You're typically told how many lines per millimeter, 260 lines per millimeter. But I need to know this number, d. What is the spacing between lines? I want you to cogitate, how do I get from the lines per millimeter to the spacing between the lines? Think about that. Take a second. I'll be back. Well, think about this. If I had 1 line per millimeter, okay, these things would be 1 millimeter apart. If I had 2 lines per millimeter, okay, so if I double it up, the distance between them is just going to be 1/2 of a millimeter. If I have 3 lines per millimeter, the spacing between them is going to be 1/3 of a millimeter. If I have 4 lines per millimeter, the spacing is going to be 1/4 of a millimeter, and so on and so on. And so you can see, if I have 260 lines per millimeter, the spacing between them is going to be 1/260 millimeters. So 1/260th of a millimeter. Now notice, that's 1/260, the quantity, millimeters, not 1/260 millimeters. That's going to be some inverse length. I don't know what that means. So it's 1/260, 1/260th of a millimeter. And of course, I could convert that into a decimal. Next question is this. If you put on the rainbow glasses and I shine my laser pointer on the screen, and the laser pointer has a wavelength of 530 nanometers, and the laser diffraction gratings have 260 lines per millimeter, how many orders of diffraction will you see? M is equal to 1, 2, 3, 4, etc., etc. How will that work? I want you to think about how you're going to solve this problem. Get started on it, and I'll be back. Well, since this is a diffraction grating problem, we're going to consider our basic diffraction grating relationship, which is this. The d times the sine of theta m is equal to m times lambda. And let's look at the different numbers and see what we can say about it. Well, the wavelength we know is 530 nanometers. We know what that is. D is equal to 1/260 millimeters. Now we have to put both of those in meters. So I have to convert this to meters. I have to convert that to meters. The other thing I want to look at is this, sine of theta m. As m gets bigger, sine of theta m gets bigger, but there's a maximum possible value that the sine of theta can take on. And what is the biggest value that that function sine of theta can have? Take a second to think about that, and we'll continue. Well, the biggest that that sine function can be, of course, is 1. So if I take 1 and I put it in for sine of theta m, I can calculate a value for m. And if I complete that calculation, what I get for m is I get 7.3 7.3. Now here's the thing. If I get 7.3, I can't have m is equal to 7.3 because m is an index variable and it takes on integer values. So I can have m is equal to 1, 2, 3, 4, 5, 6, 7. Those are all a thing. But I can't have 8. There is no 8 because 8 is bigger than 7.3. So I get 7 orders of diffraction. Okay, here's another problem which we're going to take a look at. Now, I would typically do this as a classroom demonstration. What I would do is I would take my laser, which has a wavelength of 530 nanometers, I would shine it at my rainbow glasses, which have 260 lines per millimeter, and I'd make a pattern of green dots on the screen. And it works like this. I take my laser and I shine my laser at the screen like so. But I also put in a diffraction grating right here, and as a consequence, I get not just the central line, but I get bright fringes out to the side. Okay, and that's the kind of situation we would be looking at. And your question to answer is this: what is the distance from the central maximum to the first order maximum, i.e. from this central maximum right here to the first order maximum, or in this picture, from the central maximum to the first order right here? I want you to think about how you're going to start this problem. Go ahead and get started. I'll be back. Is equal to 0. Well, let me give you some ideas for the steps. And first off, what I want you to do is this. I want you to sketch a top view of the system and then show the ray that makes the first order spot. And the question is this: how do you find the angle theta? And then second, given how you find the angle theta, how do you find the distance? Same problem as before, but we've just given you a little bit more structure. So take a look at those steps. Work them through 1 and 2 and 3. And I'll be back. Well, the first thing we're going to do is we're just going to draw a top view of the situation. So here's my laser beam, here's my diffraction grating, and I have the light that goes straight through. Where that hits the screen, that's my 0th order spot. Okay, so that's my m equals 0 spot right here. Okay, and then I'm going to get a first order spot out here. And let's just consider one side. That's my m is equal to 1 spot right here. So I'm looking for this angle right here. Of course, this is what we defined as theta 1. And the way we're going to find it, theta 1, is to use our basic relationship, which is d times sine of theta m. But I'm looking for theta 1 is just equal to m times lambda, but m is 1, so it's 1 times lambda. I know what lambda is. I know what d is. It's 1 over 260, just like it was before, 1 over 260 millimeters. I have everything I need to figure out what theta is. Now, once I know what theta 1 is, I can work out what the distance is, because you were told to look for not the angle, but the distance. And for this distance, this is y1. It's the distance of that fringe from the center of the pattern. And our basic relationship for that was that ym was equal to L times the tangent of theta m. So in this case, I'm looking for y1, and so I want theta 1, which I solved for, and L is just the distance from the grating to the screen, and that is 4 meters. So with all that information in hand, you can easily calculate what that distance will be. So take a second to complete that calculation, then I'll talk about the answers. So when I calculate, I get an angle theta 1 of about 7.9 degrees, and with that in hand, I get a distance of y1 is about 0.57 meters, so 57 centimeters. And actually that squares with my recollection of how that looks. Now here's a place where you can see this diffraction effect at play in the everyday life, and that's this. If you look at a CD or a DVD, I mean, do such things exist anymore? It's kind of crazy. They are kind of old school. But think back to the days when you would use CDs or DVDs. If you looked at the reflection of light from the surface of it, you will get these rainbows. And the rainbows occur because of diffraction. There's a diffraction coupled with a reflection that makes a so-called reflection grating. And it turns out reflection gratings are not rare in nature. And one place where you'll see them is in the indigo snake. Now, I'm going to have a lot to say about indigo later in the week. And indigo and its place in the rainbow. I have a lot to say about that, but definitely the indigo snake, is got this very, very interesting color, and the color is not from pigment. The color is from fine lines on the scales, and so I get diffraction from the lines on the scales, and so I get this color. And the really interesting thing is it looks at different color at different angles. It's kind of a remarkable shimmery sort of color that's produced by what's known as a reflection grating. Very, very cool. Another place where this shows up is in beetles. And if you look at this beetle right here, light shines on the beetle and I get this rainbow. And it goes from red to blue. These are the m=1 diffraction order for reflection grating on the beetle. And it turns out looking at that diffraction pattern is one way that you can characterize the beetles. It tells you something about their species and what they're related to, et cetera, et cetera. It's kind of an interesting way where you can use to identify different insects. Now, I also want to talk about a single slit diffraction pattern. And if I take light and I shine it through a single slit, I end up getting a diffraction pattern as well. And the reasons for that are talked about in the textbook, but I get this single slit pattern. And the thing we're interested in is the width of the central maximum. The central maximum has a certain width to it, and we're going to be interested in that. We have a relationship for the width of the central maximum right here. L is the distance to the screen. A is the width of the slit. Lambda is the wavelength of light. W is the width of that central maximum. Now, something to be aware of is that if you have a slit or I have an obstruction, it gives exactly the same equation. So if I took light and I shine it past a shaft of hair, as I do in the video that I asked you to watch, you get a diffraction pattern, and you can tell by the width of the central maximum how big the shaft of the hair is. It's a very, very kind of like interesting effect. Now, here's a question for you. Based on that relationship that we just saw, light passes through a slit and is viewed on a screen 1 meter behind the slit. If the slit is narrowed, what does that do to the band of light on the screen? And the band of light is the central maximum. Think about that one. I'll be back. Well, the basic relationship is that the width of the central maximum is 2 times lambda times L divided by A. A is the width of the slit, so if the width of the slit goes down, the width of the band of light, the central maximum, is going to increase. And so the answer is that it will become wider. It is B. It is B. So if I take light and I shine it past a shaft of someone's hair and I take a picture of the diffraction grating, does person A or person B have a thicker shaft of hair? And of course, if I have a thicker shaft of hair, I'm going to have a narrower central maximum. And so person A is going to have thicker shafts of hair. Let's take a look at B. And here's my question. The light has wavelength of 670 nanometers. That's a red laser. The hair is 1 meter from the screen, and the center width is 1.6 centimeters. What is the hair thickness? By the way, this is data that I took myself personally with a shaft of my own hair. And when I contribute a hair to this class, you know that that is deeply meaningful because I don't have a lot left. And giving one to you people is like, I am giving up something which is precious and rare. So that's a measure of my affection. Anyway, here's my question for you. If I set this up and I get the center width of 1.6 centimeters, what is the thickness of an individual shaft of hair? I want you to think about how you solve this problem. I'll be back. And of course, the way you'll look at this is as follows. The width of the central maximum is equal to 2 times lambda times L divided by A. A is what we're looking for. W is the width of the pattern. That's 1.6 centimeters, so I got to put in 0.016 meters. L is the distance to the screen. That's 1.0 meters. Lambda is the wavelength of light. That's 670 nanometers, or 670 times 10 to the minus 9th meters. And if I take all those numbers and I put them in my basic relationship, I get 84 times 10 to the minus 6th meters, and 10 to the minus 6 meters is a micron, so I get 84 microns. And actually that's about right for the shaft of a hair. 1,000 microns is a millimeter, and so this is like less than 1/10 of a millimeter, and that sounds about right for a shaft of hair. Now, another thing we're going to talk about in this wave optics section is thin film interference, and you've seen this before on soap bubbles. This is a still from a video Little Shop of Physics made, and we've got this soap film here, and you can see these bright colors in the soap film, and that's because of interference from the reflections from the front and the back of the film. This is a really, really interesting topic with lots of great applications. And here's one place where it shows up. This is a picture of my wife, Carol. And this is my wife, Carol here, my lovely wife, who is totally awesome and an incredibly good sport. And this is a picture of our previous dog, and his name was Pumbaa. And Pumbaa had an amazing eye shine. And the eye shine comes from this thing called the tapetum lucidum, which means bright carpet. That's Latin for bright carpet. In the back of the eye, for certain animals who are adapted to have really good night vision, there is this bright carpet. And what it does is it reflects light. So light goes through the retina, through the sensing cells, and it hits this layer. And if the light was not picked up the first time, it is reflected back for another pass. Didn't catch the photons the first time? No worries. We'll give you another shot at it. And Pumbaa had this amazing tapetum lucidum at the back of his eye. And you can see that because I'm taking a picture with a camera flash and asked them both to hold still. And they're both staring fixedly at me. And this is one of the things, like, Carol is so awesome. As a good sport, she did this and let me take a picture over and over and over again with the bright flash from my camera. Carol has red eyes. Pumbaa has these really shiny eyes, and it is incredibly bright, the eye shine from Pumbaa. And I want you to take a look at that. I'm going to go to the next picture where I've taken the brightness of the photo and turned it down, and look at the difference. Here's Pumbaa's eyes glowing in the dark, and here's Carol's, like, two little points of red here. So tremendous amount of light reflected by the tapetum at the back of Pumbaa's eyes. But the question is this: how do you make a mirror with biological materials? I know how to make a mirror with glass. I take flat glass and I put a coating of aluminum on it. That's how they make mirrors that you use on a daily basis. But how do I do it with no aluminum, just with, like, I don't know, like carbon and the other stuff that makes up your body? But a lot of animals manage to achieve this feat, including right here. This is a shark, and this is a picture that someone took with a flash camera. And if you were, like, doing scuba at night and you took this flash photo and you saw the glowing eye shine of the shark, and actually sharks have incredibly bright eye shine, I would definitely wet my wetsuit. It would be significantly wetter, although warmer inside if this situation occurred. Crazy, crazy. But sharks have insane eye shine. How do you do it? And I happen to know exactly how it's done for sharks. I read a great research paper about that, and it looks like this. So at the back of the shark's eye, there are layers of cells, and cells have an index of refraction of about 1.33. And in between, there are these layers of guanine crystals, which have an index of refraction of 1.83. And then if I look at the reflection from the crystals, here's what happens. If I look at the reflection from the front of the crystals, okay, there's a reflection there. And I look at a reflection from the back of the crystals, there's also a reflection there, because you always get a reflection at a boundary between two media where I have a different index of refraction. And you read about the index of refraction in the textbook. We're going to get back to it later and talk about what that is in some detail. But I have a difference in index of refraction between the crystals and the cells. And so as a consequence, I get a reflection at this surface, and I get a reflection at this surface. Okay, so that's the way that's going to work. Now, if I have enhanced reflection, that clearly means constructive interference. I have constructive interference between the light reflected from one side of the crystals and light reflected from the other side of the crystals. And what are the conditions under which that occurs? First, I have to talk about this idea. I'm going to get a reflection when I have light in one medium hits a second medium. If there's a difference in the index of refraction, there's a reflection. But if the index of refraction in medium 2 is bigger than medium 1, I will get a phase change. I'll have the wave flip over, and that changes things. So what we need to do is, first off, figure out, I have 3 different media. I get a reflection from the first interface. I get a reflection from the second interface, but I have media 1 and 2 and 3. I have 2 different regions of reflection. How many reflective phase changes do I get? Do I get any? Do I get 0? Do I get 1? Do I get 2? That's what we need to consider. If there's 0 or 2 reflective phase changes, and 2 times the thickness of the layer is equal to the index variable times lambda over n, where n is the index of refraction of the thin film, then I will get constructive interference. If I have 1 reflective phase change, this is my criterion right here. 2t is equal to m plus a half times lambda over n. That's the condition for constructive interference with 1 reflective phase change. And you can also use those for destructive interference. So I'm going to get destructive interference if I have 1 reflective phase change for the first case, destructive interference with 0 or 2 reflective phase changes for the second case. So there's a lot going on here, but it's very, very clear that when you're solving these kinds of problems, the first thing you need to consider is, are you looking at constructive or destructive interference? And how many reflective phase changes do you have? And let's look at an example. And we're going to consider the case of the shark. So the question is this. We want to know what is the longest wavelength for which there is enhanced reflection for the tissues in the back of the shark's eyes. And in the actual, if you look at the anatomy there, the layer of crystals is 80 nanometers thick. So I have an 80 nanometer thick layer of guanine crystals at the back of the shark's eye. And my question is this: what is the longest wavelength for which there is enhanced reflection? So to solve this, I have to do 3 steps. First off, how many reflective phase changes are there? Then I pick what relationship I need. And then finally, I have to decide what do I choose for the value of n, because that's an index variable. I want you to think about that. I want you to give it some thought, and I'll be back. Okay, first let's take a look at the reflective phase changes. At the first reflection, I'm going from n is equal to 1.33 into n is equal to 1.83. I have an increase in the index. n2 is bigger than n1, so I do have a reflective phase change here. So there's 1 reflective phase change there. If I look at the back, I have the light is in a medium of index of refraction 1.83. It's going into a medium of index of refraction 1.33. N2 in this case is less than N1. There is no reflective phase change here. And so there is exactly 1 reflective phase change. And we want to look for enhanced reflection. Enhanced reflection means I want constructive interference between these 2 different reflections. So constructive interference, 1 reflective phase change. Which relationship do I choose? Well, here I go. I'm looking for 1 reflective phase change, and I want constructive interference. I want this relationship right here. 2t is equal to m plus a half times lambda over n. So my basic relationship is this. 2t is equal to m plus 1/2 times lambda over n. By the way, n is always the index of refraction of the crystals. That's where the extra travel is. So I want the index of refraction of the crystals 1.83. And I want enhanced reflection. And the question asks, what's the longest wavelength? Now take a look at this relationship. T is the thickness of the layer. Okay, T is the thickness of the layer. And if I want the longest wavelength, if this number is big, that means I want number m to be small. So I'm going to pick for the value of m, I'm going to pick m is equal to 0, because that will give me the biggest possible value for lambda. T is the thickness of the layer. I know that. That's 80 nanometers, so 80 times 10 to the minus 9th meters. And N is the index refraction of the crystals. That's 1.83. I'm taking m is equal to 0. I have everything I need to solve for what lambda is. And I get wavelength of 590 nanometers. And here's my assessment. If I look at that wavelength, that is in the yellow part of the spectrum. And if I look at a picture of the eye shine from a shark, the reflection is in fact yellow. So my assessment is, yep, that works exactly as expected. Perfect. And this is this thin film interference. Fascinating. Shows up in lots of places in the world. And all the places where you do the thin film interference kind of questions, you'll solve using that same sequence of steps. Now, different animals have different color eye shines. For alligators, the reflection is red, and there's a wonderful picture in the textbook at the start of the optics part of the chapter with some gators kind of like lounging in the water, and that is a real picture. There was no fakery there. The person used a flash photograph, and they got amazing red eye shine on the sharks. Different animals have different colors of eye shine. Very, very fascinating. Next time I want to talk about the ray model of light, and we're going to start looking at things like this. This is a stick in water, and I can see this down here. That's a reflection of the bottom of the stick. And so when I have light hit a boundary between two media, not only can I get this kind of like thin film interference stuff, I can also get images. That's something we'll talk about next time when we continue talking about light and we introduce this concept of the ray model. I will see you then.